Welcome to the Explainer. Today we're going to completely change the way you look at the ocean. When we stand on the beach and watch the water recede, it's incredibly easy to think of it as just this simple, singular process, just the moon pulling the water around the Earth, right? But the ocean's tides are actually a vast, complex system driven by dual engines. Yes, gravity is absolutely at play, but there's this hidden, highly energetic second motor functioning right above our heads. It's a motor made entirely of heat and air, and it is physically pressing down on the oceans as we speak.
To set the stage for this, consider a line from Thomas Hardy's novel, The Return of the Native. He wrote, "Distilled by the sun, kneaded by the moon, it is renewed in a year, in a day, or in an hour." It actually turns out Hardy was far more scientifically accurate than he might have realized. That interplay between the sun and the moon, specifically the dual forces of heat and gravity, well, that's exactly what we're going to be exploring today.
Section 1. Beyond the moon's pole. So, gravity is really just part one of the story. We all learn about the moon's gravity in school, and it's the classic textbook explanation. But as our scientific instruments have evolved, especially satellite altimeters and deep ocean sensors, they've revealed that the reality of our oceans is just vastly more complex than a simple gravitational tug-of-war.
Okay, let's dive into this. The traditional equilibrium tide model, which comes from Isaac Newton's theory of gravitation, proposes a very neat, symmetrical picture. It essentially imagines two tidal bulges of water, directly under and directly opposite the moon or sun, tracking steadily from east to west as the Earth rotates. But talk to any oceanographer and they'll tell you these characteristics are clearly not what we observe in real life. I mean, the continents get in the way, the ocean floor is rough, and the actual water dynamics are way more chaotic. So scientists build complex forward tide models. These are hydrodynamical models that run unconstrained by data to try and predict exact sea levels. But there was a glaring problem with these models.
Section 2. The Solar Tide Anomaly. This brings us to a fascinating mystery in modern physical oceanography, an anomaly that completely perplexed researchers and literally challenged our very best mathematical models of the ocean.
See, when scientists ran their advanced forward tide models and compared them to actual readings from pelagic tide gauges out in the open ocean, the models did a fantastic job at predicting the lunar tides. But they noticed an anomalously large error, specifically at the exact frequencies of a solar day. At the 24-hour cycle, what we call the S1 tide, and the 12-hour cycle, the S2 tide, the models were just failing. The relative elevation error was unusually poor compared to other tidal constituents. The data was strongly suggesting that some fundamental physics, specific to these exact solar frequencies, were completely missing from the models.
Section 3. The sun's thermal motor. To solve this mystery, oceanographers had to look up. The missing physics weren't about the gravitational pull of massive bodies in space, they were about the daily cycle of solar radiation. The missing engine was heat.
And this introduces us to a completely different kind of tide. An atmospheric tide, often called a radiational tide, is a rhythmic oscillation in the atmosphere caused by the cyclic absorption of daily solar radiation. While gravity plays a tiny role in the atmosphere, the primary excitation mechanism here is non-gravitational. It's a thermal motor. The sun literally beats down on the atmosphere, heating it up in a daily rhythm. Now, what's really fascinating here is how this heat absorption is distributed. It's not just happening down here at ground level. Solar radiation penetrates all layers of the Earth's atmosphere, activating this thermal motor at almost all altitudes. Way up high, 150 kilometers above the surface, atomic oxygen absorbs extreme ultraviolet light. Drop down to between 100 and 150 kilometers, and molecular oxygen is absorbing far ultraviolet rays. Lower still, the ozone layer between 30 and 70 kilometers is soaking up standard ultraviolet. And right down here in the lowest atmosphere, water vapor is absorbing infrared radiation. So every single day, as the Earth turns, these atmospheric layers are blasted with solar energy and heat up. Let's walk through the thermodynamics of this process. Step 1. The daily insolation, the incoming solar radiation, heats the gases in the atmosphere. Step 2. Following basic thermodynamic laws, as these gases heat up, they expand. And because this heating is happening on a spinning globe, the cyclic expansion and contraction creates massive variations in atmospheric pressure. Step 3. This generates what we call migrating solar tides. Imagine massive westward propagating waves of air pressure synchronized perfectly with the sun, pulsing every 24 hours for the S1 tide and every 12 hours for the S2 tide. You essentially have a giant pressure wave continuously moving through the sky. Section 4. Pressure, Transfer, and Oceans. But how exactly does a wave in the sky solve our mystery down in the ocean? Well, we have to shift our focus downward to see how this atmospheric thermal motor actually reaches the seafloor.
So the crucial point is the hydrodynamic response. This is driven by what's called transient pressure theory and the inverse barometer effect. You see, the ocean isn't isolated from the sky. As that massive atmospheric tide propagates overhead, it brings rapid changes in barometric pressure. The atmosphere physically breathes, and as the air expands and contracts, its weight presses down heavily on the sea surface. This transient pressure rapidly forces a hydrodynamic response in the water below. The ocean is quite literally being squished and released by the weight of the sky every 12 and 24 hours.
When we map this out globally for the S2 or 12-hour tide, you can actually separate these two motors visually. By contrasting the amplitude of the gravitational forcing pulling the water versus the atmospheric pressure loading pushing the water, you get a clear picture. The ocean is responding simultaneously to the invisible pull of gravity from space and the tangible, heavy push of the atmosphere from above.
And let me tell you, this is not some insignificant push. In the global average, the atmospherically forced S2 ocean tide is 14.7% as large as the gravitationally forced S2 tide. Nearly 15% of that 12-hour ocean tide isn't caused by gravitational pull at all. It's caused by the pressure loading of the atmospheric thermal tide.
And this brilliantly illustrates why those earlier forward ocean models were failing. The atmospheric S2 tide differs from the gravitational S2 tide by about 194 degrees in phase. They aren't perfectly synced up. They hit the ocean at entirely different times. When scientists finally took this atmospheric pressure data, which was derived from 13 years of operational analysis fields, and added its forcing into the hydrodynamical tide models, those anomalously poor error rates just vanished. The model's accuracy for the S2 tide improved to match all the other tidal constituents. The missing piece of the puzzle was the weight of the thermal tide.
Section 5. Gravity v. Thermal tides. To really solidify our understanding here, let's bring these two distinct planetary engines side by side for a final synthesis.
Let's move to a complete mental model of the ocean's behavior. On one hand, we have gravitational tides. These work by pulling water, they're driven by the mass of celestial bodies, and they are lunisolar, meaning both the moon and the sun contribute to them. On the other hand, we have thermal tides. These work by pushing water via the inverse barometer effect. They're driven by daily insolation and thermodynamics, and they are strictly solar. One is an invisible pull, the other is a tangible atmospheric push of expanding heated air. Both are absolutely crucial to the rhythm of our planet.
Which leaves us with this final thought. We are so conditioned to look up at the moon when we think of the tides. But the next time you look at the ocean, I want you to think about the sun heating the air around you. Can you feel the rhythmic weights of the atmosphere breathing on the sea? Understanding the true complexity of our world makes it all the more beautiful. Thanks for joining me for this explainer, and keep your curiosity fired up.